gonna remove mine, and you will plug the HDMI cable to your laptop, and that will be it. Yeah, you wanna try it? Wanna try it now?
Let's try.
Oh, let's try it.
Just to be sure.
All right.
Okay. Good.
I can do it. I can do it. Perfect. Οπότε είναι μια χαρά. Θα έχουν το δικό τους λάπτοπ, από ό,τι φαίνεται. Απλά να... Λοιπόν, μια χαρά νομίζω είναι.
Εγώ νόμιζα ότι θα ήταν ο κάποιος. Πέρσι ήταν ο Δημήτρης ο Καραολάνης.
Ναι. Έχει ήχο, ωραία. Εδώ φαίνεται off.
Αχα, ναι, σωστά. Για ποιο λόγο σημαίνει αυτό?
Τι γίνεται, όλα καλά?
Θέλει επιλογή.
Εδώ, αυτό.
Τώρα λογικά...
Όχι, είναι ακόμα με χ το βγάζει κάτω δεξιά. Σαν να είναι σε σίγαση.
Under such conditions, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible. Now we are looking at the detector playing on the monitor. Bright spots appear here and there. These spots indicate individual electrons.
Εντάξει, δεν πειράζει.
Electrons are sent out only occasionally.
Θα τα πω εγώ.
Therefore, the chance of finding one electron in the microscope is very small.
Ναι, περάστε το. Δεν το ξέρω, πρέπει να δούμε μόλις έρθουν
να κάνει την παρουσίαση ο Σάμι. Αυτή την αρχική παρουσίαση που είπαμε,
ναι.
λίγο για τη σχολή,
ναι.
να έχουμε και ένα περιθώριο 5 λεπτών μετά.
Ωραία.
Λοιπόν, πήγε εκεί πέρα, δεν πειράζει, θα το βάλω στη μέση της οθόνης για να μην μπερδευτείτε. Εδώ.
Ωραία, οπότε είναι αυτή, έτσι.
Είναι αυτή εδώ πέρα πάνω.
Τέλεια.
Και ό,τι άλλο θέλουν μπορούν να βγάλουν, αν θα πάρει το στικάκι.
Ωραία, τέλεια. Ευχαριστώ.
Τι έχει?
HDMI.
HDMI. Φέρνω το. Μπορούσα να βρω και το iPad να συνδέσω, αλλά τέλος πάντων.
Λοιπόν, έχετε μόνο ένα PDF.
Ένα PDF, ναι.
Έχει θύρα HDMI.
Μήπως να το κάνουμε το iPad καλύτερα.
Σας βολεύει, απλά να έχει
HDMI.
Έχετε adapter.
Από αυτό.
Πολύ ωραία. Ό,τι σας εξυπηρετεί.
Θα βγει αυτό το κομπιούτερ ή
Αυτό το κομπιούτερ ναι, θα βγει για να βάλετε το δικό σας. Θέλετε λίγο να... Ας ξεκινήσουμε. Ακούγομαι. Okay, good evening everyone. Welcome to the American Farm School. With great honor, we welcome you to the second Balkan summer student gathering here in the American Farm School. It's an honor to have you here with us for a second year in a row. We are very excited to host you here and to spend the week with you. We hope that you enjoy your time here, that you have a wonderful time exploring and learning new things during this summertime before school starts. But without further ado, let's begin because we need to carry on with our schedule. My name is Sami Arslan and I'm going to be presenting just a short introduction so you can get a feeling of what the American Farm School is. But before we begin, I would like to ask you, is there any of you that has ever been here before? Or is it your first time? Let me see those hands. Okay, so just a bunch of you have already been here before. For the rest of you, is it your first time? Okay, that's good. Special welcome to all of you. We're excited to have you here. I heard that some of you don't come from Greece, you come from a different part of the world. Do you want to share where you come from real quick? Let me hear the country you come from. Don't be shy. Serbia. Yeah, what else? Montenegro, yes. Turkey, wonderful. Albania, wonderful. Moldova, Macedonia, wonderful guys. Special welcome to all of you. We would like to just say a few things so you have already been here in the American Farm School for a few hours. Some of you have already spent a night here. But I would just give you a brief notice of what the American Farm School is about. I'm just going to tell you a few things about the history because we are talking about an institution with more than 120 years of history. Since the date of the beginning from Dr. John Henry House, who is the founder of the American Farm School. He came here in Thessaloniki and he started he began something new. He put life into his vision, which was to create something new, to create and give opportunities to the young generation to do things in the agricultural sector. So he came here, he bought a land, this part of Thessaloniki, which was a dry and empty land, absolutely nothing apart from nothing. And he cultivated it, he put effort into it, and he started teaching young people how to be stewards of what they had in their hands. And now you're gonna be wondering how this farming and all this stuff, how do they connect with what we are interested in, with physics, with labs, and all these things that you like to do. Well, guys, think about that here in the American Farm School, we have 750 acres of land, which is the lab that the students use on a daily basis. All this campus that we have in our hands is what is the lab that the students use on a daily basis. So they don't just contain themselves inside of a space, inside a few walls, but they have this whole land to explore and use so they can learn new things about science and stuff. But this is just the beginning. Let's take a look of what we can do here in the American Farm School, what students do on a daily basis. First of all, let me tell you that here in the American Farm School, we have students of all ages, started from kindergarten and going all the way up until high school, vocational high school, junior college, and college. There's a lot of opportunities for students to learn different things. Apart from that, there are areas of this campus that you probably have already explored, or if you haven't already, soon enough you will do. So we have many science labs, we have libraries, sport facilities, restaurants, students' residence, areas where students can explore and get experience in the field. We have wineries, we have smart greenhouses that they use modern technology, so everything can happen automatically without needing to put effort. The greenhouses work on their own, and other interesting stuff. You will have your time, you will go around in the campus, and you will see all this stuff. But let me tell you a few things about the reality of what students actually do, starting from the vocational high school. So this is where students emphasize on the plant production, animal production, and food technology. So what do they do? What does it mean when we say that they study plant science? Do they just spend time on the fields? Yes, they do. But what do they do? What do they actually do? They learn innovation and different things that technology provides these days. For example, you see this agricultural drone. The students have the opportunity to see how that works in real life. What do they need to know so they can operate a machine like that, so they can cultivate their land? What is the technology? What is the science behind it? So they will be able to have better productivity in their job. And not only that, but also there's other application in animal science where they can use technology. For instance, right here, with the use of special colors in the animals, they can use technology again, and they can use the GPS and have an understanding of where their animals are in real time. They can locate them, and they can also get information about their health and other things regarding each animal. Other than that, for sure, we get into the field of food and the technology of food here, more focused inside labs, where you will do different interesting stuff with chemical compounds and all these beautiful things that chemistry has blessed us with. So here, apart from the labs, there's also there's parts of the campus, such as the milk factory, where the students can actually see not only where the milk comes from, but where we put the milk. How do we process the milk? How can we produce something that comes from milk? All the technology and all the science that leads to the final product. So when it comes to food science, which is a very interesting science, students will learn what food processing means. They will learn what quality control means, and they will see with their eyes what all the science behind it. They will also dive into more interesting fields such as new food development, and I'll tell you in a bit how they produce their own foods, or they experiment with stuff that they haven't done before. So this is one option. The other option is the regular high school, where students can follow the three directions that are provided at the moment in the schools. They have the science and health. There is the economics and computer science, and also the humanities studies. All of that is an option for the students that go to the general high school. And apart from that, there is also a great emphasis not only in their hard skills and what they can learn and all the knowledge they can obtain, but also in their soft skills, on how they can improve the abilities and the skills that they already have. Some of these soft skills, you will soon realize that they are very, very important for the future, no matter what direction you will choose to follow in your future. So all of these soft skills that you see on the screens and more are stuff that are being cultivated here, because what the school, the American Farm School, cares about, and what the vision of the founder of the school was, is to cultivate the human and his inner self. So the students are going to learn how to cooperate, how to develop their skills, their leadership skills, and more stuff like that. Not just learning, which they will do. They will learn the basics, and they will dive deeper into science, but they will also dive deeper into their inner selves, and they will cultivate their inside, whatever there is inside of them. So this is also a great focus here on the school. And apart from that, there are many opportunities for the students that finish school here. Apart from as I already told you, participating in different science labs, they have different projects that they boost their desire, let's say, for entrepreneurship, to do something new, to create something new, to create a new product, to create a new business, and all this stuff. Of course, the environmental education, the environmental production, and let's not forget to mention all the sports activities. Probably you have already noticed all the football pitches and the basketball courts and the gym and all this stuff that there is here. Of course, we care about this stuff as well. And other than that, there are many opportunities for the student to travel abroad, as you already do. Some of you have traveled to come here to experience something new. The students here have the opportunity to do that, travel abroad, go to different countries, see different cultures, learn new things, and widen their horizons this way. And of course, opportunities for their studies, as we have the opportunity to have a program called Study USA. I will tell you in a bit a few more details about that. Of course, many participation in different programs, many participations in trips, many participation in competitions. Some of them you can see on the screen. Whoever has willingness to follow, opportunities will be given to them. And also not only in science, not only inside a lab, but also outside in the campus, taking advantage of all this nature that we have available in our hands. Here we see some of the projects that the kids had on the entrepreneurship projects, where they created this smartwatch that you can see on the screen. They created it, they designed it, and it's called smart because it has the ability to detect the sound waves. So it's designed for someone who has a disability in their ear. So they can wear this watch, and every time there is a sound wave coming, this smartwatch is gonna buzz, so the person will understand that there is somebody honking or shouting on them, or there's a noise, so they need to be alert. This is just an example. They have projects like that every year, and as I told you, they produce their own products. For example, you see these jars are some jars that they are part of their snail breeding. What do? They cultivate, they also process, so breeding the snails, and after that they use what they take so they can create their own products. These are some gels, these are some things that are actually edible because they are snail fillet. So if you're brave enough, you can go ahead and try this. And many more stuff. They spend a lot of time out in the field, as I told you, exploring. This is a 750 acres land where this is actually their lab. It doesn't contain them in just one small room with 4 walls, but they have all this land to experience all that. Of course, the students enjoy their time not only outside and inside the labs, but they also do different activities such as sports or other cultural activities, different clubs that has to do with arts, have to do with drama classes or anything you can imagine. They also participate in other competitions, for example, the MUN, the Model of United Nations, where they have the opportunity to develop their skills on learning how to defend themselves, how to defend their country, and to bring arguments in front of hundreds of people. So very interesting stuff. They also do a lot of volunteer work whenever the opportunity is given, different trips, a lot of stuff that helps them bring new experiences to develop new understanding for the world around them, and also an opportunity for them to open their horizons for their future, to study. There's the program that runs here in the American Farm School for over 10 years now. And we have more than 100 students that they have already, they have been sent to the United States with a scholarship to fulfill their dreams. So this is something that the American Farm School provides. Here we see some of the students that graduated this year, and very, very soon they're going to be starting their journey in the United States as young students. So there's also the opportunity for this to happen for anyone who is willing and wants to do something like that. Of course, the American Farm School is well connected with many departments, many universities all over the world, and many different businesses, not only in Greece, but also across Europe. So there are many opportunities for someone graduating from here, getting well connected with the existing market. Many things, many different areas, many different opportunities there is for someone who is willing to pursue their future. I could be sharing with you more and more details about how a day-to-day life look like for the student that study here in the American Farm School, but I wouldn't like to take more time. I would just tell you a few things about our programs. After graduating high school, there is the college, Perotis College, which also provides some undergraduate and graduate programs. They're all English programs, so anyone, it welcomes every year students from all over the world. You can see here in the screens what are the programs that run these years, undergraduate, and of course master's programs, mostly in agriculture, but also in business and digital marketing. Apart from that, there's also a junior college where there's also options for someone in 2 years to study, to get some basic but fundamental knowledge for something very specific in the agricultural sector, and continue their career or just get straight into the market and begin their professional journey. Other than that, one last thing that I would like to say, and I will end with this, is that there are endless possibilities on what you can do. You have the freedom to decide which direction you're gonna choose, what path, what dream you're gonna pursue. But the truth is that whatever it is in your heart, whatever it is that your heart is burning for, if you truly desire it, if you truly live for this, and you have one specific goal in your mind, it's for sure that if you put the effort and the time, I'm sure that this will pay off, and I'm sure that you will succeed no matter what the world says. I'm very grateful that I got this time to share a few things about the American Farm School. I wanna thank you for your time. I wanna thank you for your patience, and I wanna wish you a wonderful time and a wonderful week here in the American Farm School, full of new experiences, a lot of knowledge, much fun, Hopefully, don't forget that we are here to learn, but also to have fun and enjoy our time here. So thank you for your time and enjoy your time here in the American Farm School. Thank you very much.
We'll start immediately. Please note that there's not going to be any interval. Anyone that wants to get some rest and have a coffee or drink some water may step outside. We have some small bottles of water. So let's start. Dear President, BBU President, Mr. Wagner, dear friends, dear colleagues, students and parents, thank you very much for being here. Welcome to the second Balkan Summer School. This school is organized by the Balkan Physical Union, the Hellenic Physical Society, and the European Physical Society, and of course, Ελληνογερμανική Αγωγή. On behalf of the Hellenic Physical Society, I would like to thank the distinguished speakers who will be sharing their knowledge with us in the upcoming days. I would also like to thank the colleagues, the mentors, and all the students who traveled many hours from across the Balkans to come to Thessaloniki. I would also like to thank the members of the organizing committee for the valuable assistance. This school is held under the auspices of the Department of Physics of the Aristotle University of Thessaloniki, the municipality and the region of the Central Macedonia. I would like to thank the co-organizers, the European projects FAITH, PICO, and Discovery Space, which are bringing Nobel Prize-level science into school classrooms. Dear friends, since 2022, Thessaloniki has been hosting the headquarters of the Balkan Physical Union. I hope that by the end of this summer school, you will feel in Thessaloniki as if you were at home. I wish you a wonderful time in Thessaloniki. Thank you very much. Now I would like to ask Dr. Christos Ritsulis, Vice President for Academic Affairs of the American Farm School, to deliver a greeting.
Dear friends, thank you very much for being here. I hope that you will enjoy the stay here and you will enjoy the theme. Something like about many, many years ago, I came across in one of my undergraduate classes on quantum chemistry and the Schrödinger equation. And what was this? That was a very funny, strange-looking mathematical entity. And the more you delved into it, the more complex and beautiful it became. And it appears that such roots hold the keys to understanding the basis of nature. So I come to wonder, this is a very practical institution. We are basically wanting to apply things. Do such things really matter? The answer is yes. They should be the subject and the object of our desire, because these are the foundation of the world we're living in. And we should study and understand things like quantum physics, not only because they can interpret the world, but because basically they appear to be the world we live in. So if we want to understand the list of the general auspices of physics, even I would dare say in politics, we should have to, in geography, we should understand the fundamental aspects of nature. And I think that if we can simply define the very key to the fundamentals of nature, quantum physics is certainly one of them. So I urge you not to look at funny equations as I wrongly did once, but to look as an opportunity for a true window to the true nature of things. So I would like to thank all the esteemed guests who are here, and I would like to wish you a very, very pleasant and constructive stay. Thank you very much.
We should thank you, Mr. Ritsulis. You should know that since 2015, Hellenic Physical Society has implemented many activities in this school. The first Greek summer school started in 2017. the first Balkan Physics Olympiad, the first Balkan Summer School, so we do feel like home here. Thank you very, very much. Now, I would like to invite the new elected president of the Balkan Physical Union, Dr. Sophocles Sotiriou, to deliver a short greeting and start, let's say, being the chair of the first session. Mr. President, thank you very much.
Dear Kostas, I have also to thank you for your great effort. I think you share with us a great vision to transform Thessaloniki to the capital of science education of the Balkan countries, and you have achieved this in a very, very short time. And we really appreciate your efforts and your great passion, because I think this is the most important behind, let's say, the organizations and the different names are the people who are making the difference, and they are bringing the quality to what we are doing. So I would like also to thank the American Farm School. It's really a great place to host such events. It's the second year. Last year, the school was devoted on astronomy and astrophysics. Now we are taking the chance and following, let's say, the major initiative of UNESCO, focusing on quantum science and technology, to organize a course on quantum physics. So we are really, we are in a paradox, especially I know that we have here students and teachers from many countries, but at least here in Greece, we are experiencing a great paradox. The interest in science, and especially in physics, is dropping with a very big speed the last years. And this is obvious, let's say, not only from the international results, the scores in PISA, or all the performance of the students in the school is, let's say, from it clearly presented from the numerous empty places in the physics departments of the country. And this is a major problem, I would like to say, especially for all of us who are focusing on physics education. But I would like to say that there are key messages from all around the world, also from top innovators, very important people in the field of technology, who are giving a different message, that we have to focus on the basic principles, on the structure of the natural world. We have to focus in physics. And this is, let's say, I have my presentation, and I think all the presentations will be shared with all of you. And Vidya is one of the pioneers in artificial intelligence. And when they have asked their CEO if he was 20 years old, what he will choose as a subject to study, he said that he will not focus on software and coding, but rather on physics. And this is, let's say, also the message from Elon Musk recently. These are statements made last June. And he said that it's not only mathematics. The question was related about the significant value of mathematics. He said that it's also physics along with mathematics. And he said this is the key to building scalable innovation. And this is what we are talking about here. Also, I would like to share this. This is from a book from Umberto Eco, a great philosopher, He, in his book, he's presenting, let's say, his opinion really against the magical view of science that we are trying to introduce also in our classrooms. That suddenly Galileo saw the lamp in the chair moving, in the church moving, and he finally discovered that there are numerous things connected with that. But science is not working like that. It's a completely different process. And everybody, starting from the school classrooms, have to understand that there is no some magical view. It's a very long and a very difficult process to discover what is happening out there. And let's say, based on that, we have tried really to design a program that will introduce the students step by step in this process. So our course is including a number of, let me see how this works. No, never mind, let's say the light blue color is related to the lectures. With the blue, we have the workshops. We have designed a number of workshops of the key experiments that introduced back in 1920 the researchers and the scientists in the quantum world. And also, we have planned a number of activities, visits and opportunities, let's say, to communicate with each other and also to visit the beautiful city of Thessaloniki here. So it's very important, let's say, for us to demonstrate the nature of science, the nature of quantum physics in the framework of this school. And at the same time, to promote all these skills that were mentioned also before and this school is promoting, like critical thinking and problem solving, especially introduction of in complex problems and ways and methods that are out there to follow. So this is the key characteristics of the scientific methodology that we would like to introduce in this course. So as I said, we are celebrating this year 100 years of quantum science and technology. The first paper that has introduced the term was published back in 1925. It was written in German, and it has introduced the term quantum mechanics. So this was done from Bohr and Jordan at that time, and it has included, let's say, a number of issues related, let's say, to what was known up to that point, let's say, to the specific moment. Key questions are the ones that they are going to be the starting point, the trigger, let's say, of our exploration in this summer school. The wave or the particle characteristics and when they appear. Is the light a wave or a particle? Are electrons, protons, particles or waves? And when they are presenting a different behavior, when we are trying to investigate their nature. There is a very nice book from Richard Feynman. It's called Six Easy Pieces. In the sixth one is describing, let's say, this different character of particles and waves. And we will try in one of our labs to present, to follow the whole process as it is described in Feynman's book on this introduction. We will start by throwing small stones on a double slit, and we will see what is expected in the frame behind. Then we will deploy this system in the liquid, and we will see what is the phenomenon presented in the frame behind, and then we will move to the microcosmos, and we will see what is happening when we are shooting, for example, electrons to the target. We will discuss phenomena that are taking place in the sun, and they are making, let's say, a sun sign. This is based completely on quantum phenomena, like quantum tunneling, because it's really impossible to bring two nucleus together because of their very strong electric force, even in the very high temperatures of the sun. So how this is happening to our sun, but also to all the stars in the sky? We will also, this is how we can say the model of the sun, of the operation on how sun is producing energy, and you will see that sun is the source of electron neutrinos. Neutrinos, we are calling them, is a word that we have to avoid, especially in science, to use, but it's so, let's say, so strange particles that we are using this word. We are calling them ghost particles. So there is a very strange phenomenon that neutrinos, while they are traveling from the sun, and as they are approaching Earth and they are start interacting with the matter, they are changing their nature, and they are being transformed to other kinds of neutrinos. It was a major problem for many years to measure the exact flux of neutrinos coming from the sun. And it was really very difficult to find what was happening. And of course, this was a very specific phenomenon that was, let's say, its explanation was presented by Bruno Pontecorvo back in 1970s, called neutrino oscillations. So the neutrinos are, in principle, they are composed of three different, we can say, states of neutrino: the neutrino, electron neutrino, muon neutrino, and tau neutrino. And while they are traveling in the matter, they are changing, they oscillate. A particle oscillate. It's changing its nature and it's being transformed to another particle. And I will close because we have to hear many things. This was just a small appetizer of what is going to follow. So with the photoelectric effect and the major contribution of Einstein in the explanation of this phenomenon, and again, here I'm presenting this paper. At that time, Professor Bogner, German, was the key language of scientific development, especially in quantum physics. So most of the papers were written in German, and of course next to it is the translation of the first paper that was published at that time. There was a phrase that is really introducing this a completely new way of thinking that Elon Musk was speaking about in his small interview in last June. And we see this in this phrase. It's the first time that someone is saying that the light, the energy of a light wave emitted from a point source is not spread continuously over ever larger volumes, but consists of a finite number of energy quanta. So this is the introduction to the quantum world. And of course, the emission of spectrum of atoms that formed the Bohr model later back in 1926, introducing us, let's say, to the whole structure of the microcosmos. So with this small introduction, I would, let's say, I would like to initiate the keynote session of our summer school. So I would like to ask Professor Anastasios Petkou from the Aristotle University of Thessaloniki. He's going to talk to us about what is quantum physics. He's the director of the Laboratory of Theoretical Physics at the university, Aristotle University. He's teaching quantum mechanics and mathematical physics, and his research fields are quantum theory, string theory, quantum gravity, and critical systems. Dear Professor, thank you so much for being here with us.
Why it doesn't work? Extent. No. So why is that not working? Δεν το κάναμε. Τι έγινε πριν και... Το δοκιμάσουμε να το ξανακάνουμε. Δοκίμασε λίγο. Πριν μου έβγαλε εδώ κάτι, αλλά... Το iPad. Content, ναι, εδώ. Αυτό ήταν. Okay. Okay, so thank you very much for the invitation. I wish to thank Kostas Bourlias and the Greek and Balkan Physical Union for this invitation to speak in this event. I hope that it works. Come on. Why it still doesn't work? Πριν δεν δούλεψε. Όχι, όχι, αυτό, choose content. Αυτό, window, αυτό το κάνω. Ναι, 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 choose window wrap, mirror this window. Αυτό έτσι δηλαδή, και αυτό πρέπει να το έκανα τώρα, ναι. Τώρα παίζει. Τώρα, άμα κάνω το view full screen mode, αυτό ήθελα. Γιατί δεν παίζει full screen mode. Να το κάνω έτσι. Να το ανοίξω έτσι. Α, ούτε αυτό. Ούτε αυτό. Entire screen, μήπως πρέπει να κάνουμε entire screen. Ναι. Οκ. Το full screen mode, ναι. No. Okay, finally, I'm sorry for that thing. Okay, I wish again to thank Kostas Bourlias and the Balkan and Greek physical unions. I think that it's a great opportunity for us and for you also, for students from all countries in the region, young students, to first of all to get to know each other this week here, and secondly to get to know a little bit about physics and what is the current research in physics. I hope that you will enjoy your week here, and I hope that you will go back to your countries or to your schools here in this country, thinking more positively about physics and believing and getting the idea that physics, studying physics, is fun. In fact, as it was mentioned before, I am a professor in the university here. I teach quantum physics, and my research is in quantum physics, string theory, elementary particles, fundamental physics, and all this stuff that you may have read in some books or in the news. And I hope that, as the Professor Sotiriou said before, I hope that you will also start understanding or appreciating that physics is the fundamental science in the sense that it has to do with the physical world. Everything in the physical world is physics. If you noticed, we are in the American Farm School, and okay, I will do again a last thing so that I will not have to open my screen again. So we are in the American Farm School, and sometimes when I go and talk to young children about physics in the elementary school, and I ask them, well, what is nature? They tell me nature are the trees, are the plants, you know, the cows, etc. And then I ask them, is my computer nature? They say, no, this is not part of nature. No, nature, environment is all this stuff. But, you know, we physicists are so strange people that we think that our computer, this thing here, and the plants and the animals are made of the same electrons, the same atoms, They are just built in a different way, but they are actually the same. So physics studies everything, the plants, nature, whatever, and also the computers and everything else. Of course, with the help of mathematics. If one thing you get from my talk is that physics and mathematics are the best of friends in science. Okay, so you have heard also that this year, 2025, is the year of quantum physics. Because, as was shown in the previous talk, in 2025, the term quantum mechanics appeared in some journal, in some scientific journal. But the term quantum appeared a little bit earlier, as I will just review a little bit. And we think that, some people think that this was the biggest discovery, at least of the previous century, in the field of science. Why is that? And what is quantum physics, which actually is so different from what we would call classical physics? So the outline of my talk, will be a little bit more explanatory, not many equations, actually very, very few equations. But you can ask me later, or I have a more detailed version of my talk with a little bit more equations. Or you can visit the web page of Aristotle's University Laboratory of Theoretical Physics, where we do very interesting stuff, and this talk will be uploaded there. And I will give you the link to this web page. So, okay, classical physics. Why we call it classical physics, like we call classical everything that has to do with the past. Here in Greece, we are very happy, we are lucky that our ancestors built the Parthenon or other classical antiquities. Okay, so classical physics is a little bit like that, and I think it is summarized in this saying by Laplace, Pierre-Simon Laplace, and I think it was Laplace that the guy that was asked by Napoleon why he wrote, I think, a very interesting book about celestial mechanics, how the objects move in the cosmos and the universe, what they knew. And he was really the guy who tried to formulate everything that was known about physics at that time, in the 18th century. So, the present state of the universe, like the fact that we are here now, or what is happening, everything, depends only of what happened, last minute, or, a few years ago. So we can explain everything that is happening now if we knew what happened yesterday, or a minute ago, or a year ago. This is something that we all have inside us. We think that something happens because a minute ago, or 2 minutes ago, or a second ago, or an hour ago, something else happened. So this is completely determined by its past history. So there are two main principles of classical physics. This is not, physics is sometimes related to philosophy. In fact, as you may also know, Aristotle, who was born near here in this region, was the natural philosopher, the guy who was philosophizing about nature. And I think he was the one who started this discussion, this connection of philosophy and physics. One of the guys, at least. So what are the classical principles? The principles of classical physics. So every physical quantity has a well-defined value, independent whether I measure it, I know it, or I don't know it. I will just tell you what this means. And then the second is called determinism. It means that if I have a physical quantity, whatever that is, a system, an atom, a person, a bird, everything that I need to know is there. So if I am very clever and very good, I can understand what is happening there. It is something that we all like, and we think that it's correct. For example, as Einstein was saying, because Einstein did not believe in quantum mechanics, actually made very, very big efforts to kill quantum mechanics, but unfortunately, as nobody is perfect. So, for example, Einstein said, I know that the moon now is somewhere, I can calculate, and I'm sure that the moon is there. I don't observe the moon. If you go out, it's sun, there's the sun, the moon maybe is from the other side of the world, of the earth, but I know it is there. Everybody knows it is there. We are absolutely sure it is there, okay? Well, quantum mechanics actually challenges this belief, not only challenges this belief, but proves that this belief is wrong. So quantum mechanics is very strange. Okay. Now, a little bit of mathematics for those of you who may have seen this or may have read some of this stuff. As I said before, physics and mathematics, they are very, very good friends. And it is impossible, from my point of view, to do one without the other. Actually, mathematics you can do by itself, but it does not have to do with the physical world. It's just a game, a mind game. If mathematics blends with physics, then we have reality and real science. So in classical physics is based on Newtonian mechanics. Newtonian mechanics starts from a few simple laws. One of the simplest one is the so-called Hooke's law, that the force is actually proportional. And here I made a mistake because I have to have a second derivative actually on the force of the spring is proportional to its elongation. So, okay. I will try to be closer. So the force is proportional to x. The bigger the x, the distance from the equilibrium point, the bigger the force that pulls the spring in. And this force, as I wrote in the second line, is proportional, as we say, to the second derivative of the position of the particle. I think some of you may know what is a derivative because you are in the last year of your high school. So this is like the second variation of the position. And the fact that this derivative of the position is equal to a force In fact, you will learn, if you go to the university in physics, you will learn that this is also related to what we call the relativity principle, and general relativity is nothing but a generalization of this principle. So, okay, now here we go to more deep stuff, and I don't want you to learn this stuff by hand, but just see the last line here. You see, okay, again, historically, why these people in the end of in the beginning of the 20th century, in 1900, starting from Laplace and many, many other great scientists, why did they believe that everything was classical physics? Because they had, as we say, a very nice formulation of everything around us. You know, they were looking at the phenomena. For example, they were throwing bombs in the world war, in the wars. They were flying, birds. They were looking how the birds go around. They were observing the planets. All this was in a mathematical formulation what was called Hamiltonian mechanics. And they thought that if we are able to solve the equations of Hamiltonian mechanics, which are some equations, you see, the last equations before the last line I have are first derivatives. First derivative of something is equal to something else. First derivative of something is equal to something else. These are two equations with first derivatives. I think some of you may have even solved this kind of equation. It's not very difficult. You take the integral. Maybe you have learned also about the integral. This is why you learn derivatives and integrals in high school, to solve this kind of equation. And if you solve these equations, you know the motion of everything. So these people believed that if we are very clever enough, and if we have the mechanism, the patience and the intelligence to solve this kind of equations, we will know the motion of everything in this world. And this is a very beautiful formulation that we still use now in many ways. People fly satellites, maybe you've heard about astrophysics. Astrophysics is nothing but Newtonian equations. It's like that. It's very interesting. Shokonda, okay. Nearer, I'm sorry for that. Again. Okay, and then came the revolution. The revolution came, I think, and some other people think, in 1900, when Max Planck introduced quanta, or black body radiation. Okay. Now, let me tell you a little bit of the story here, and why I think this was, in my personal point of view, the biggest discovery until now in human science. Why? Because Max Planck was a classical physicist. He knew everything. He was, one of the best physicists of his time. He understood how to solve these equations, etc. And then he had in front of him an experimental result. What is the experimental result that he had? Maybe you know, or maybe you have seen in movies, that when the commandos want to go into the dark in the night, they wear some glasses that they can see at night. Why they can see at night? If we close the lights in this room and we make it dark, and I wear the glasses, I can still see you. Why? Yes, please. There is radiation which you see, but so you emit radiation. You are radiating. So every body or body or object radiates. Everything has radiation. So, in fact, even black body radiation is the radiation that is not affected. For example, I see you because light comes to you and is reflected, and I see you because of light. But then if there is no light, why I see you? Because you radiate by yourself. You are αυτόφωτος, not heterophotos, for example. Okay, so they knew that every object, every material object radiates. And they wanted to make sure that you have an object that radiates without having any other external source. So they made very ovens like the ones that we bake our pies and our food. And they were measuring what comes out of the oven, what radiation comes out of the oven, without external radiation, so that it's a black body radiation. Okay, with the calculations of classical physics, it was an easy problem, well, not so easy, to calculate what is the radiation that comes. And if the temperature goes up, the radiation, the frequency of the radiation goes up. It was a straightforward calculation. And if you are a good student and you know your classical physics, you can do it. But then the experiments were not like that. The radiation was going up. When they were heating the oven, the radiation was, the frequency was going up, and then it went down. And, it must be a problem because we are very good students, we know classical physics, we solve our equations, but they made some mistake. So for many years, many people said that this is a mistake, and we cannot explain it, but we will explain it. But Planck, after struggling, said, okay, let me do a crazy idea. Let's assume that what you radiate, what this guy radiates, what this oven radiates, is not electromagnetic waves, but is the so-called quanta, which he did not know what they are, but they are not waves, they are quanta, small quantities of energy. Here I have the equation. The energy of each quanta is h times omega. Omega is the frequency. He had to introduce h. H is a number. It has this value. And this is a crazy idea. Nobody believed him. There is no reason. The classical physics does not tell him to do this. But it was the only way to explain physics. What I want to say with this story, and why I think this is so important. Because you see, it doesn't matter how clever you are and how clever you are solving equations. Because physics is about explaining what is there. If what is there, does not follow from your equations, then you have to follow what is there. This is reality. So quantum mechanics was imposed on us, was not discovered. It's very different from actually what Einstein did. Einstein discovered general relativity by making Gedanken experiments in his mind. There are two completely different approaches to physics. The way they do. That's why Einstein never understood quantum physics, and that is why many people, even now, very famous physicists, Nobel Prize winners, they don't believe in quantum mechanics. Still, they write papers that quantum mechanics is wrong. Because quantum mechanics is something that is imposed on us. We just observe it, and there is no other way to explain it other than quantum mechanics. So that happened in 1900, and in 1905, as it was shown before, Einstein used or 1902, maybe I'm wrong, but it was, I think, 1905, explained the photoelectric effect using the photons of Planck. And then there was a very big progress where Bohr actually explained the fact that the atomic spectra are discrete. I will not go into what is this, but anyway, Bohr made the atomic model. And then Schrödinger wrote his equation. Born gave the probabilistic interpretation. Heisenberg showed his uncertainty principle. Dirac showed his equation. And there was an immediate progress in this direction. And even later, when the Second World happened, quantum mechanics was combined with special relativity, not with general relativity. In fact, this is the biggest problem in our in physics. We cannot combine quantum mechanics with gravity. Probably they are incompatible, but that's another story. And anyway, quantum mechanics with special relativity was combined to what is called quantum field theory, which is what we study from then and what we use to study the elementary particles, the accelerators, what we study at CERN and in other places. Quantum field theory. Now, I told you about the principles of classical physics. Now, what are the principles of quantum physics? It took many years, many decades to understand what are the main principles of quantum physics. The first principle is called the superposition, which, again, this is very strange, and I think I will explain a little bit about that. A physical system can exist into a linear combination of states. Maybe you know what is a linear combination, but I will explain if you don't know. And then the other principle, which is called complementarity, is that if I know, if anybody knows, this Hamiltonian, how the particles move, like what we wanted to know. We want to know how particles move. If we know that, the system is not quantum. There is no quantum mechanics. Finito. There is no quantum mechanics if we know the particle trajectories. It's incompatible. It's very weird. In fact, this seems surreal. What do I mean by the fact that the physical system can exist in a linear combination? It means that the moon that I don't see now can be a full moon or, half moon, a crescent. Or a person, when I want to say, this is a person, this person, is person A plus person B. Okay, this is too extreme, but in fact, we observe this for quantum mechanical systems. We observe this kind of behavior, and this is the only way with which we can explain the experimental results. So, a concrete example. What is the most simple quantum system that you can imagine? And how one thinks about quantum physics in everyday life. So you think about the roulette. This is the simplest, if you want, quantum mechanical system. This is the way that if you want to do quantum physics, you have to deal with physical questions. So, what is the roulette? Maybe you know it, maybe you don't, but this is what it is. It's a system that we know when you go to the roulette, you know all the numbers. You know how many numbers the roulette has. I don't know how many. I don't know, suppose that it has, 50 numbers. So I know all the numbers. Then what I also know is the probabilities if I throw the ball, what is the probability that I will get one number? I know it. Somebody tells me. For example, in this roulette, in the usual roulette, the probabilities are equal because the slots are equal. If I had a roulette, half of it was, number one, and then small pieces, the other numbers, you would say, it's very possible that if I throw the roulette, it will go into this one number. But here, it's all equal. But, I know the probabilities. Then, when we say that we observe the system and we make a measurement and we talk to our friend and say, what did you measure? The energy of this, thing is this. What is this? We throw the ball goes into one of these systems, and we get the measurement, one of these numbers, and we get the measurement. But there is always the possibility that if we do it again, it will go to another one. There is always the possibility that if we do it again, we'll go to yet another one. So we are not sure that we will get this answer. Almost never. So going back to the moon, well, we know that the moon is somewhere there and it will appear in a few hours on the sky, but we are not sure 100%. It may or it may not. Now, of course, now you will ask me, and of course many people ask, this is completely crazy. I can calculate for you that the moon will appear at this time, and it works, ever, all the time. Yes, of course, because I told you that if you know the classical path of the moon, there is no quantum effect. So quantum mechanics splits the world into two parts. One is what we call the macrocosm, that has to do with us and with things that we observe, and this is classical physics. And the other one is the microcosm, the electrons and the atoms and all the other small stuff that we have, that are the microphysics, that make the microphysics that we have to understand with quantum mechanics. How the two are connected, how I go from macrophysics to microphysics, is not yet understood. It's an open question in physics. But we know that quantum mechanics works in microphysics, small distances, and the classical physics, of course, works in. So what I want to say is that if these numbers are, for example, the position of a particle, so you ask me, what is the position of a particle? Is 1, 2, 3, whatever the particle moves. In quantum mechanics, if this is a quantum particle, it can be in many, many positions, in all the possible positions, and if I measure one position, it's because the ball went into this position with some probability. So keep this in mind as the simplest quantum mechanical system. Now, I think I will skip this, but just for fun, I will. Even the simplest quantum mechanical system is a system that it's like a roulette that has actually two slots, 1 and 2. And this is actually called a qubit. I think you will learn more about that in the next days of this school. Just 2 slots, a roulette with 2 slots. Now, this is very simple, and actually the mathematics of that is very simple. We can do it. And I think in the next years, actually, people in the high school, we will do the mathematics of qubits. It's very simple, but it is also, as you may have understood, you may have learned, it is very important, because if we knew how to make a qubit, we would have made a quantum computer. It's not easy to make a qubit. If we had a qubit here, this is really the most powerful quantum computer that you can have. And the mathematics are not so difficult, but you need to understand how to extract information from this qubit. So, now, this has to do with one of the weird things about quantum mechanics, and maybe you have heard also about it, which is the Schrödinger's cat paradox. Of course, you know, people were clever. When Schrödinger wrote the equation, people were asking him, you know, what is this? You are telling me crazy things. How this is possible to happen? And so Schrödinger indeed created this paradox, which still until now is unresolved. But people understand it a little bit better now. So if you have a cat in a box, and the cat in the box, in the box inside, imagine that there is some, well, Schrödinger said it's a radioactive substance. So if the cat touches this button, you have radioactivity and the cat dies. You can think about many possibilities, many other variations. But then if you do not open the box and there is a cat there, how do you know that this is dead or alive? The only way to do it is to open the box and see if it is dead or if it is alive. But before opening the box, if I want to tell you, what is the cat? Is it dead or alive? The only thing I can tell you is half dead or half alive. So, if you remember what I was telling you at the beginning, classical physics tells you that there is always an answer to the question, what is the state of the system? What is the state of the moon? Where is the moon? The moon is there. Now, what is the state of the cat? Dead or alive? Well, I don't know. If I assume it is dead or alive, I will not make the experiment correctly. So, the quantum world is based on the fact that the state, the description of a system, allows for many possibilities. And then when you make the observation, you go into one of the possibilities and you find this result. But you could have found another result with some probability. Well, these are the paradoxes that are with us for 100 years at least. Now, let me tell you something more concrete and actually much more practical and fundamental. Not more fundamental, sorry. Everything is fundamental, but it's more practical. And something that you may not have appreciated. You have heard about Heisenberg's uncertainty principle. That everything is uncertain, and et cetera, et cetera. This is actually the Heisenberg uncertainty principle is the basic fact that keeps all matter together, is responsible for the existence of the material world. Think about that. When you learn about the atomic model, you learn about the protons and the electrons. And then, of course, you ask the question, well, it's positive and negative charges, why this doesn't follow? Well, okay, they tell you people who do classical physics, you see the moon and the earth, of course they attract, but the moon doesn't follow because it rotates. But okay, but imagine, okay, well, this is not the right answer, but imagine that you have a proton and an electron. They don't rotate. They just try to, bring them together. There is no rotation, so this thing with the rotation doesn't work. So, of course, they attract. Positive charge, negative charge. So how all this nature behind us with protons and electrons, imagine that the beginning was just protons and electrons floating around, coming together because they attract. Everything vanished. But atoms created and they are stable. The electron does not fall into the proton. And of course, the larger atoms here with many electrons and many protons, they do not collapse. They are stable. Why? Because of the uncertainty principle. Because the uncertainty principle tells us, if you look in these equations, P is the momentum, and momentum, is mass times the velocity, and A is somehow, the distance of the box in which the particle moves. So the uncertainty principle tells us that the product of the momentum times the distance where the particle moves is constant, which means that if the momentum is big, the distance is small. Or if the distance is small, the momentum is big. So when the electrons come very close to the, to the core, to the proton, for example, to the positive charge particle, they are confined into small distances. So the momentum must be large. So they start moving around. So they don't fall into the core because they have to move. If you shoot something directly into the moon, it will go to the moon. There is no way that it can circle around if it does not have any angular velocity. If you shoot an electron to a proton, it will necessarily move. It will necessarily go around. And then it will go around and it will create an atom. It will create a stable entity because of the uncertainty principle. And this is the basic reason why, the solid matter exists. It's the uncertainty principle. And actually, if you go even at smaller distances where we find the protons, the quarks, you see that they have much bigger energy. That is why we have to go to CERN to smash the protons with very high energies to find the quarks, which we do not find free, but anyway, to see what is there. Because they have very, very high energy. They move very, very fast. They have very high momentum. Because they are confined into a small distance. And this is the uncertainty principle. So it's very important. Well, now this is another, the final thing that I wanted to say about the weird quantum world, but you need some more quantum knowledge for that. But I can describe it because this is also very important. Now, what you see here is the state of two electrons or two quantum systems, which I named 1 and 2. Now, I will not explain to you what is this, but in quantum mechanics, if we want to describe two electrons, which, as we say, are entangled, we describe them like that. And what do we understand from this description? We understand that if I measure some property of one electron, then I immediately know some property of the other electron. Now, what are the properties of the electrons? The properties of the electrons are the so-called spin, which is again a very difficult, it's a quantum property. Spin does not exist in classical physics. Sometimes people say that the electrons go around like that, but this is completely incorrect. Spin is a quantum property of the electron. That is why Dirac got the Nobel Prize. But there is a very weird phenomenon which Einstein actually pointed out. I told you Einstein tried to kill quantum physics because Einstein indeed pointed out that, look, you tell me this very strange quantum mechanics, etc., but this has this very strange property, which I don't think is correct. If I give you two electrons which are very close here, actually I produce them. I just do something and I make two electrons or two photons. And then I let them go away. I wait. One electron goes beyond our solar system, goes to the other side of the universe. The other electron stays here. Nothing, no problem with that. Then the guy, somebody who is in the other side of the universe, measures the spin of the electron. Again, you don't need to know what is the spin. Measure the spins of the electron. Then here, myself here, me here, I know exactly what is the spin of my electron. Which means that this guy who is over there has communicated from the edge of the universe to me the information about the spin of my electron. I know that if I measure this electron, I will find like that. And it's correct. I will find it. So Einstein said this doesn't happen because from the edge of the universe, the information, the light to come here, it will take million light years. How do you know that? Well, quantum mechanics actually tells you that this happens. So the story is that this was proven experimentally in situations not from the edge of the universe, but in the Earth. And people got the Nobel Prize in 2022. It was proven in the 80s. By 3 people, anyway, and many other people have proved it. So this is a very weird phenomenon, quantum entanglement, which we still do not understand why it's happening, and we do not understand how to take advantage of that. Because imagine that we could take advantage of that and actually exploit it. One of the things that probably you will listen here is that if you had a code which is entangled, a system, two systems. I have a code here, which is a chain of numbers, but this system is entangled with another system somewhere else. If the system is somebody tries to break in to change the code, I will immediately understand that there is a problem. And I will immediately change my code, my password, so it will make it impossible to guess the password. It will be the perfect crypto system. Because every time you try to enter into my system, I will understand it immediately. You don't have the chance to enter into my system. But okay, this hasn't been achieved yet. Okay, finally. Now, quantum mechanics, we find it in our everyday life. Okay, these are some things that you probably also know. Okay, here I have the toaster. Toaster is black body radiation. You see that the resistance in the toaster changes the color according to the temperature. And this is what I described to you before. This is the black body. You can think about the black body. And the color is the frequency. And the fact that the frequency has a behavior as the temperature changes, a behavior like a bell. The frequency goes up and then it goes down as the temperature goes up. This is the black body radiation, which is explained only by quantum mechanics. There is no way that classical physics can explain that. The other thing, of course, quantum mechanics is everywhere in our computers, is in our semiconductors. You may know about computing, which is just a very efficient way to make 0-1 codes in 0-1 language, Boolean language, and to making questions and answering questions. So the big technological advancement was that these gates were made very, 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 very small. And so the gate 0 and 1 means that I have a system that passes electricity or not, like a switch, but very, very, very small. Now, what is this system? This system is a quantum semiconductor, and the only reason why this semiconductor exists is quantum mechanics. It's a quantum system. And of course, I don't need to tell you how important that is. The other thing that is very important are the photovoltaics. Photons come from the sun, and they move the electrons from the insulating band to the conducting band, and we create a current. This is very important and very interesting in everyday life. Lasers are the other example. Again, have to do with emission of photons by bands of material. And of course, what we teach also in our, these things we teach in our classes. We also teach the basics of magnetic resonance. So when you go to do a magnetic resonance, what is the picture that you get is actually the spin of the electrons of the water, usually. At least in the past it was the water, how much water is concentrated in a particular part of your body, and you take a picture of that. You put a magnetic field and you can split the spin and you get a picture and you understand how much water has in this part of your body. And this is theory. This is something that was developed, in the 1930s already. Okay, so I will finish by telling you that in the future, many people believe that the future will be quantum, in the sense that there is a lot of interest in developing technologies like quantum computing, as I said, quantum cryptography, quantum sensors. This is very important. So I want to finish by saying that quantum mechanics is actually, in my personal point of view, is the most important theory that we have to explain the microscopic world around us, the fundamental world around us. And it has many technological applications, and we hopefully will see many of them in the future. But it's not only that. As I was trying to say, quantum mechanics also challenges our perception of the world, of the reality. So what is real? What is not real? Can we have, two things entangled? Can we have information from a distance? So these are very, very important questions. And they become even more important if we try to combine quantum physics, quantum mechanics, with general relativity. This is one of the biggest challenges in modern research in theoretical physics. And I hope that some of you will be attracted to this field. I want to say that our area people, scientists from the Balkan area are very active and very good into this theoretical physics. I have many colleagues in Romania, in Bulgaria, in Serbia, and in Turkey, and in smaller countries. They are emerging now, who are actually also very good scientists, not only in the area, but also in other places in the US and Europe. And I hope that some of you will follow into their steps and continue the good work. So thank you very much. Okay, good. Okay, τα βγάζω αυτά. Πήρα μαζί μου, εδώ τα πρέπει. Εδώ είμαστε. Όπα. Άστε να τα πάρω αυτά. Συγγνώμη. Ωραία.
Την εργασία του κυρίου Τάσο. Ναι, την εργασία του λέω.
So, thank you so much for this presentation and also giving the Balkan perspective of quantum future. So, thank you so much, Professor, for the presentation. Our next talk will focus on, let's say, on the trip from atoms to quantum information. Professor Ioannis Antoniou from the Aristotle University of Thessaloniki. He has more than 20 years of experience in teaching the theory of chaos, mathematical modeling, quantum information at the Department of Mathematics of the Aristotle University. And his research work includes more than 300 publications in the field. Thank you so much for being with us here to share your experience.
Thank you very much for the invitation and also the local organizers. Θέλω την έξοδο σε HDMI. Ρεύμα δεν θέλω. So, it is very nice to be here, and the Hellenic Physical Society and the local organizers have done a magnificent job. So, my presentation is somehow a natural continuation of Professor Petko's presentation. And I will try to address 4 points. What is information? Why quantum information? The answer to the weirdness of quantum mechanics has been understood by the end of the previous century, and the answer is quantum probability. We did not understand quantum probability before. Now that we know it mathematically, quantum mechanics is not weird. Weird is our attachment to classical notions. We somehow are attached to the notion of objective, pre-existing reality. Nobody knows what is reality. We assume that reality pre-exists, and then we measure what is pre-existing. This assumption is wrong. We like it or we don't like it. It is wrong. Why it is wrong? It's not a philosophical argument. Assuming that quantum reality is objective, you arrive in contradictions with the assumption of quantum mechanics. And whenever whenever someone tried to contradict quantum mechanics, he was wrong. I will be more specific on the way. So the weirdness is not quantum mechanics. The weirdness is our attachment to classical notions. I hope that now we are not so much attached to classical notions as we understand better what is quantum mechanics. So what is information? I have more information than somebody if I can predict more. For example, Thales of Miletus predicted the solar eclipse on the 28th of May, 585 BC. He predicted precisely. He knew something more than those who were ecstatically observing the sun becoming black. So Thales has some information. We don't know precisely what he had and how this information was available, but when we say that I have more information than somebody, it means that I can predict more. Conversely now, if I say to Thales that I can predict the solar eclipse, am I giving him some information? Please. No, I don't give him. He knows also how to predict. I'm not adding anything to his information. Yes? So, if I give information to you, you should be surprised. New information means more surprise. If I say something trivial, you will not be surprised. You will very politely listen to me. And then when you go out, they will ask you what he said. He said nothing. We knew that from the high school. So this idea of information goes back to two persons, Kolmogorov, the founder of probability, and Wiener, the founder of cybernetics and one of the co-founders of quantum mechanics. So information, I get information means I receive messages which I cannot predict. This definition is clear and it becomes precise mathematically, and now it's the subject of what we call information theory. Originally, information theory comes from statistical mechanics, classical statistical mechanics by the end of the 19th century, the notion of entropy. So information can be quantified. How? By the amount of surprise. Straight and clear. So when you have more information, it means that you are less bored. Information means it's not boring. Now, information is represented as messages. And messages are sequences of symbols. These symbols are registered in memory. No memory, no information. If you forget what I said, communication is futile. We both lose our time. Information is transmitted or communicated via channels and processed by machines we call processors or computers. Our brain is a processor. Yes. Brain, it is clear already by 1930. The neurons, the synapses, and so on. And when this was decoded, artificial intelligence came out. Artificial intelligence is mimicking the way the brain stores and processes information. And you will be surprised from the fact that the key idea of the neural network was based on the Ising model of magnets. That's why the Nobel Prize in Physics was given to this discovery. It's not very much known, but it was very helpful for the physics community, Professor Petku, because it gives new possibilities for our students. So, memory, channels, and processors require two things. The hardware, it means the material which is understood and constructed using physics, and the software. What is the software? The series of instructions in the form of algorithms and written in programs. Without this, you cannot process information. So these are the characteristics of information. In all systems you can imagine. Even our mind is processing information respecting these facts. The Antikythera mechanism, which was discovered in the beginning of the 20th century, is an information processor? Yes. It can predict eclipses, it can predict astronomical events, and so on. All this information is encoded in the mechanism that you see. A copy of this you will see in the Science Museum here in Thessaloniki. Babbage constructed in 1850 the mechanical computer where the hardware which implements the software is pre-programmed. Pre-programmed. Pre-programmed means the way that the mechanical parts are linked is such that the result of the calculation is predetermined. So, ladies and gentlemen, if we were working with these machines today, the modern processors, how big should they be? Many times the surface of our planet. So with mechanical means, there are very serious limitations which make it impossible to work with mechanical machines. So they try to exploit electronic devices, semiconductors, which Professor Petku mentioned before. This is the first electronic numerical integrator and computer. Constructed in 1945, here you see von Neumann, the guy who actually invented the architecture of computers, of classical computers. What is the novelty here? compared to the previous computing machines, the mechanical ones. The novelty is that it is programmable. I cannot change the program of the Antikythera mechanism without changing the mechanical parts. With this computer, I can do it. So it was a big, big step. This doesn't matter. So you can change the program without changing the hardware. This is the big novelty. So what happened afterwards? We started to write programs in order to solve equations. So I have different equations from Professor Petku, and we write different programs. When I was undergraduate, I spent a lot of time writing programs in Fortran or C language. It was fun, but I felt very bored. Today, do we have to write programs? I'm addressing this question to the students. Are you obliged to write programs? Say it. Yes, you are very polite and very diplomatic. I speak straight now. There is no need to write programs. Artificial intelligence machines will do it for you. Who says that? Not me. Chang and other heads of artificial intelligence business suggest students to not lose time to learn programming. Programming is boring. Artificial intelligence will do it for you. Instead of writing codes, you should focus on understanding the question, specifying the results that you need, and learn how to discuss with the machine. Say it. More loudly, please. Louder. Louder. Do you know anything perfect in this world? No. Friends of mine in businesses fire the programmers and they keep those who can check the result. So you're taking a lot of money to write a program. After you write the program, it is not coming in the market before some expert will check it. This is the guy that has future today. To be the guy who checks the programs, whether written by humans or by machines. You are right, machines make mistakes, but you can learn how to teach the machines to prevent some mistakes. For example, we gave the exercises of mathematics department, the examinations, and asked the machine, ChatGPT-4, to solve them. All were wrong. We corrected it, and we taught the machine what was the mistake. Then we asked a friend to ask the same question to the machine. They did not make this mistake. You are also learning it this way. I'm also learning it this way. The key remark here is that ENIAC was programmable, in contradistinction to mechanical machines. But now this programming is not necessary thanks to artificial intelligence. Boring activities are not necessary anymore. We are free from this boring process. So humanity needs the guy who can check the program and give correct instructions for the specifications of the program. You can see many such discussions in the internet, for example, in several sites. This is the flow chart that von Neumann wrote for this computer. And now I would like to mention what is a flow chart. It is a diagram of actions which represents a workflow. For example, you start with the problem that lamp does not work. Then you ask the question that is if lamp is plugged on. If no, you plug the lamp. If yes, you change the bulb and so on. So every flow chart has a beginning and end. And the missing links are the things that you learn from mathematicians. These are implementations of theorems, existence proofs, or construction of results. And now, if you know this, you can use artificial intelligence to ask the machine to write the program for you. All processors that we mentioned so far operate on classical hardware and software. They used quantum mechanical principles, but the processing of semiconductor devices are classical. Classical means the way information is encoded. So why quantum? Professor Petcu presented this in a clear way. I will add a few remarks in order to pave the way for the information. What happened at the beginning of the 20th century is that we realized it was, in fact, forced upon us that matter and light behave in a non-classical way. What this means? First, matter shows interference like wave. Interference was discovered by Jung in 1804, and it's when you throw light in a pattern with openings, you have this nice distribution of intensity behind the screen. And this cannot be interpreted with the Newtonian view of light. Newton believed that light consists of corpuscles, of particles of light. This cannot give such interference pattern, so after Jung, it was accepted that light is a wave, like the sound wave. Now, what is an electron? If you throw electrons through a cathode ray, it behaves like a beam of particles. Using Newton mechanics, you can predict everything. But if you throw electrons through two holes, the two-slit experiment, be careful here, if the opening is small enough means at the order of the diameter of the electron, then you realize interference pattern. So if electron is a particle, it gives you the upper distribution of intensities. If electron is a wave, it gives you the lower distribution. So how can an electron behave like a particle in the cathode rays And like a wave, in the two-slit experiment, what is the electron? A particle or a wave? This question is a paradox in the context of classical physics. It is not a paradox in quantum mechanics. Why it is not a paradox? Because quantum mechanics says what Professor Petko emphasized as well, the properties of beings do not pre-exist. They are specified according to observation. Practically speaking, you do not ask what is an electron. You ask what is an electron if I observe it that way. So observation in quantum mechanics is not just I define the observable, I call speed or velocity or position. It means I define the observable plus the operational way to observe it. So quantum observation is classical observation plus the statement about the observation process. That is not understood by classical minds. Classical minds disconnect the properties from the way we observe these properties. Professor Petko mentioned the example of the moon. There is a famous article in Physics Today. Is the moon there when nobody looks at it? Answered by Viktor Weisskopf, Nobel Prize winner in nuclear physics. Ask a foolish question, 3 dots. What is the foolish question? That you ask about moon without specifying the way you observe it. If you play with questions, if you play with physics by just asking questions about ontology, you arrive at contradictions. Then you say, quantum mechanics is weird. It is not weird. Our minds are weird. Why? Because we do not ask the correct question. And the correct question is the way I observe it. You ask this question, there is no contradiction, there is no mystery. No mystery at all. Everything is understood and predictable. Statistically, probabilistically, but predictable. So, the fact that light is absorbed in discrete packets of energy is an experimental fact when we analyzed the emission of radiation from the hydrogen atom. And the Bohr atom was modeled on this fact. It was very successful. Spectral theory, spectroscopy and later spectral theory was developed using this initial point. Schrödinger was a very erotic person, and he had an artistic nature. So he visualized atoms as musical instruments of light. So as you play the guitar and you have the distinct frequencies, light plays with the guitar of atoms. So he founded what we now call wave mechanics. Einstein discovered that light is a wave, but it is emitted and absorbed in lumps of energy. Some mini wave packets, he called them photons, and the conclusion from this observation and the previous one is that both light and matter behave like waves or particles according to the way we observe them. If you don't add this statement, quantum mechanics is a weird, magical theory. You add the way of observation and there is no magic. It's manageable and programmable as well. Now, what is quantum probability? Quantum probability is a way to assess the uncertainty of lack of predictability of events. If you can predict everything, then you do not need probability theory. If you cannot predict everything, then you need a way to assess the amount of ignorance you have, to assess the uncertainty you face in front of you. And the only tool that we know so far is probability theory. So, classical probability assumes that the states are points, points in some space of elementary events. For example, in roulette, the events are the 36 plus 2 numbers. So the space of events is 38 points. In quantum mechanics, states are vectors. Why? Because otherwise there is no interference. I give this cheap answer, but the real answer is lying in the interpretation of the black body radiation. Professor Petku said that the distribution of spectral intensity with temperature is not explainable in terms of classical physics. But if you assume that radiation is absorbed and emitted in discrete lumps of light called photons or quanta of light, everything is okay. Logically, this means that if I accept quantum mechanics, I can explain the black body radiation. This is well known. What is not well known is the converse. The converse is a theorem proven by Poincaré later. It's a very famous result, which was reproduced in English and commented in several, at least 3 journals I have seen. What is this statement? If you have the black body radiation, the experimental form of the black body radiation, can you conclude quantum mechanics? Does quantum mechanics follow from the black body radiation? Yes. It was proven by Poincaré. It's a very astonishing result, because somehow this excludes other interpretations of black body radiation. Black body radiation is a message from the universe to humanity. Be serious, now you are in the realm of quantum mechanics. So it is necessary and sufficient. Please go to the internet to search the famous Poincaré converse theorem. In classical probability, events are encoded as subsets. In quantum mechanics, events are vector subspaces. In simple words, bundles of vectors. A quantum event is mathematically represented as a bundle of vectors. Once this is said, you can define probability. Kolmogorov proposed 3 axioms of any probability theory. First, it is a map from events to the numbers between 0 and 1. 0 means impossible event. 1 means certain event. So probabilistic analysis includes deterministic analysis. The first is that the probability that something has occurred, it means that anything can happen in the phase space, is 1. This whole sample space is the certain event. The probability that an event, an empty event happening is 0. Empty event is impossible event. Now, I would like to ask you a question. If the sun, I suppose the event that the sun will not rise tomorrow, is it an impossible event? I'm asking you, say it. No. Why? Some UFO may come, something may happen, there can be a fog, so I cannot see the sun. The probability for this event is very low, extremely low, but it's not impossible. Correct answer. The third axiom of Kolmogorov is additivity. Additivity is that the probability that two disjoint events will happen is the sum of the probabilities. Disjoint events means that one event has no connection with the other. So if you have, for example, the probability that the roulette will give you 9, and I throw a coin and it comes head. The probability of both events is the sum of the two probabilities. That is the axiom of additivity of Kolmogorov. So if you have these three axioms, you have a probability theory. Kolmogorov did not tell us how we construct the probability. He said, however you construct it, using frequency, using guessing, whatever you do, you have to respect these possibilities. All probabilities theories share and accept these notions. They have constructed different probability theories. They are useless. Nice mathematical constructions, but useless. Now, in quantum probability, you repeat Kolmogorov axioms, but the events are the vector bundles. The bundles of vectors, the vector subspace. That's the only difference. And when you say that two events are disjoint, you mean that two vectors are orthogonal. That's the only difference. Ladies and gentlemen, when you accept these axioms, everything follows in a mathematically clean way. No contradiction, no paradox, no weirdness. We did not know that before. Before means before, let's say, 1990. After 1990, everything became clear. No mystery, no magic. All theorems proved from these assumptions of quantum probability gave correct predictions. Correct prediction means testable experimentally and found to be correct. We give you a few examples now. The simplest example I could imagine is the finding a coin in the pie, in the New Year's pie. You put the coin somewhere, and then you cut, and you find it. What is the probability that the coin is in this direction or the other direction? Classically speaking, what you do, you calculate the angle, phi. And you find this probability. If to be in the vertical axis, phi is the angular distance from the axis, horizontal or vertical. But the count probability is the square of the projection. It's cosine square. So it is not the angular distance, this one, phi. It is the square of the projection, the definition. And then you make the predictions. The red line is the classical probabilistic prediction. The green line is the quantum probabilistic prediction. Mathematically, they are both correct. So I cannot argue mathematically. I ask the experimentalist. Someone is doing the experiment. If he finds the red line, then he says, this effect is classical. If he finds the green line, he says, this effect is quantum. Full stop. Mathematically, I cannot decide what is correct. Mathematics tells you what are the consequences of your assumptions. Mathematicians do not argue the assumptions. Who is giving to them the assumptions? The guy who is discussing with nature. Who is this guy? The physicist. So mathematician needs the physicist to get the assumptions. And then he makes the calculations to get the results. Now, there are many consequences which are the subject of many courses in quantum mechanics. I will mention 3 consequences mentioned also by Professor Petku because they are crucial. Crucial means they have business interest as well. Do not underestimate the business interest. Whatever you do should have some result which can interest society. So you can live with this work. So Heisenberg uncertainty follows from this simple observation of Heisenberg. The electron trajectory is this one. I already made a mistake. I said the electron trajectory, as if the trajectory pre-exists. Nothing pre-exists unless I observe it. So if I observe it with the first light beam, the red one, the electron momentum hits, the photon momentum hits the electron, so the trajectory that I will observe is this one. And if I throw a second photon beam, I change even more. What is the trajectory of the electron? Tell me. You cannot tell me unless I specify to you how I observe it. This shows why the classical notion of pre-existing orbit is meaningless. Meaningless. If we shut the lights, do I exist? Can you see me? No, you cannot, unless you have an infrared camera. So, to see me, you need a scattering process of light on my body and then to your eye. So this is a fact of life. And if we do not take this fact into account, we have no connection with reality, but we can write philosophical papers that how weird is quantum mechanics, how weird is reality. Weird is the fact that our mind is stuck to pre-existing notions. That is the most weird thing for me. Schrödinger cat. Is the cat dead or alive? So quantum mechanics predicts that the cat is a linear combination of living cat and dead cat. What is the weird thing here? That this cannot exist. But whoever says this does not understand quantum mechanics. Why? Because the wave function of the cat is not an objective part of reality, but an assessment of my knowledge of the cat. Be careful here. The wave function is not an objective characteristic of reality. This was the subject of many hot discussions, more than 1,000 papers were published about this. The issue is finished. Why? You assume that wave function is objective, you arrive in contradictions. It is done, finished. It's a mathematical fact. So what is the wave function if it is not objective reality? Wave function is an assessment of reality. No contradiction. So if I know nothing but the wave function, I will give you the probability that the cat is alive and the probability that the cat is dead. How? As I gave the probability for the location of the coin in the pie. The same way. Schrödinger introduced this fact and understood this as not as a paradox, but as a resource. And today, in quantum computing, this is a computational resource. Quantum Schrödinger states are not magic. They have been constructed operationally and utilized to make money. Schrödinger states, Schrödinger cat states, they are called. Entanglement is the last point. Entanglement is a fact that two different entities cannot forget their common origin. For example, when you meet two particles the same way, in the opposite direction, the total momentum is zero, the total angular momentum is zero, and this means that they are entangled. They don't forget how they are created. I will ask you, especially the young students, if you have an intensive love story, and then everything, the lady goes away, do you forget the common experience? No! Many years later, you see the lady, and nice thoughts come to your mind. The same story as photons. Schrödinger gave the name entanglement because he appreciated these love stories. He was a famous lover as well. And Schrödinger said that entanglement is the quintessential feature of quantum mechanics. It means that the most important fact. Entanglement appears without physical interaction. It is a statistical relation. We call it quantum correlation, quantum non-separability. It's the same story. Is it useful? Practically. There are no quantum computers without entanglement. All quantum computation is based on the entanglement. All. It is the most precious resource of quantum processes. The experimental confirmation of entanglement started in 1986 with Elena Spey and his group, but there were many mathematical loopholes. And the followers of Einstein protested. Several experiments followed, which confirmed completely the prediction of entanglement, and the Nobel Prize, as Professor Petku mentioned, was given 3 years ago for entanglement. Entanglement is the base of quantum computation, of cosmology, of quantum sensors, of quantum networks. Quantum internet is not anymore a dream or a vision. It is reality in the market. There are theories which are based on entanglement to understand how our mind works. Sociology, economics, there are many applications. Economics, Morgan Stanley, for example, has a group in quantum computation. They don't spend their money for fun. They know what they are doing and why they invest their money. Many pharmaceutical companies do the same, of course. Now, all this is nice, but the final point in practice is, can I exploit the possibilities of quantum theory? Can I use atoms and molecules as information registers? Because the semiconductors do not encode information in one atom, but in many billions of atoms. This was proposed by Feynman and others who are presented there. I have the references as well, you can check them. They dreamed, they visualized that this is possible. No experimental result. Why? Because suppose you can encode information in atoms as qubits. Can you program the qubits? Programmability is a concept introduced by Toffoli. I would like to thank Mr. Tsounakis for this valuable information. They introduced the notion of programmable matter. Von Neumann had no reason to introduce this concept because the matter he used was programmable. Obviously. The matter based on semiconductors that Professor Petku mentioned was programmable. But are atoms programmable? Which means, can I write several programs to be processed by the same array of atoms and information encoded in individual atoms? Not trivial. It was the result of hard work to realize this. And this was realized because it was proved that individual atoms can process information. The Nobel Prize in Physics in 2012 was given to Harose and Wineland for this discovery. Processability is possible at the hardware, the quantum hardware level. Not trivial results. That is why everybody is crazy with quantum computing, because it is very solidly confirmed. It is not just the imagination of Feynman and his friends. That is why investors are not reluctant to invest their billions on this business. And the construction of quantum software was also rewarded by society, these guys, this breakthrough physics prize. I stop at the most interesting moment. What is next? What has been done with these fantastic possibilities? I stop here to conclude three things. First, how quantum processing operates. Secondly, it is not weird at all. And thirdly, it is experimentally confirmed and programmable. Tomorrow, Mr. Tsounakis will tell us what happened afterwards. The mathematics of quantum mechanics is a bit weird. Weird means if you are accustomed to sets and you don't know vectors and matrices, it's weird. If you know them, it's not weird. But Bob Koche and Abramson from Oxford used the theorems of Penrose, discovered in general relativity, to represent quantum process with diagrams. Diagrams which simplify the flow charts. The flow charts that I showed you before are very simple for checking the lamp. but very complicated when you have 2 million instructions. The quantum software is much easier and can be simplified using the diagrams. We translated the book of Bob Koke. We have started an initiative on quantum computation at the high school level at the last 2 years. It works very well with high schools in Greece. It is done every Saturday morning from 11 to 12. And last year we implemented this diagrammatic language. This diagrammatic language will be presented tomorrow by Mr. Sarigiolis, who translated the book in Greek. And you will see that you can process quantum algorithms without knowing higher linear algebra, by understanding the Penrose diagrams adapted for this simple quantum mechanical case. Simple for Penrose compared to what he did in relativity. And the third thing is quantum games. Entanglement is not only a precious resource for quantum processing. It inspired games. All classical games have a quantum mechanical counterpart based on entanglement. The coin. You can play quantum coin. You can play quantum roulette. You can play quantum chess. Of course. And in the quantum chess, some possibilities are given by entanglement. So you have to think not only the classical chess, but the quantum chess. Tomorrow we can, if the organizers will give us the time, Professor Voulias, we can try to play quantum games, many quantum games. This Mr. Kosmidis will present tomorrow as well. So it is high-level business, high-level entertainment, and high-level understanding of reality. The future belongs to you. Thank you very much.
Thank you so much.
You are most welcome.
So many more things to come.
Yes.
Yeah.
We have seen nothing.
Yeah, we have seen nothing, or we are just at the beginning.
Yes.
Let's say. So, thank you so much. The two keynotes that we had up to now are focusing on, let's say, scientific discoveries and the presentation of the quantum science from atoms to quantum information. But let's say the challenge here is to bring the world of research and the world of education together. So we have to create, it was mentioned before, we have to create a synapses between the world of science and the scientific research at this high level with education. So the third keynote talk is focusing on science education. And we have here with us, he has traveled all the way from Bavaria to present his long-lasting work for numerous years. Professor Bogner has great experience, let's say, in assessing the students' interest and motivation and trying to demonstrate how the technology is able to increase the interest of students in science, even in such complex issues related to quantum mechanics or the invisible world. So his record includes more than 400 publications in the field. He has received many awards in Europe and in US for this, and he's here with us tonight to present how we can visualize the invisible in science education. Professor Bogner, thank you so much for being here with us.
Hello, everybody. Sorry, I'm the last obstacle for the dinner, but I try to make my long story short to about half an hour. And I try to bring you over a little more biology, because by training I'm a biologist and a chemist. Also, in the last 20 years, some physics guys tried to turn me over to a physics one. And I tried to take over the physics guys to biology. So why I'm here? Because I'm the coordinator of this space project, where we try to introduce artificial intelligence into the classroom. In the very last of my talk, I will come back to this, and you see some of the people here in the audience. On the left one, it's me. The second one is Sophocles. And we are working now in the third year about this project. So let me start with a quotation. It's a quotation 25 years ago, where somebody mentioned that the computer, the role of the computer. Of course, I cannot go into the detail here, because you are a generation already growing up with the computer. When I did my PhD, the first computer came up. It was the Commodore 64, and I needed 3 disks just to write my PhD without any figure. It was just the beginning. So, making the invisible visible. I think this is the key message for bringing in computers into the classroom. Most of you know this stupid game. That means you have to guess what is the message of this girl. And it's sometimes it's a long game, because the guessing is not easy. Oops, something is wrong, yeah. All of you know this experience. The experiment is in the Deutsches Museum in Munich. And I have been several times there. And most of the class, the physics classes, were very happy to send the physics teacher in this cage. And of course, we know that he will survive. But when you do this with augmented reality, you could visualize why the physics teacher is surviving. Another example. This were the Google classes 20 years ago. And it's me 20 years ago. And it did not work without 2 technicians in the background. Nowadays, Google glasses are everywhere. By the way, I have another one too. Sophocles, also 20 years ago. It was a project 2004 until 2006, where we introduced augmented reality into the classroom. Just an example. Here, for example, somebody is throwing a ball, which is an everyday thing, but then simultaneously the ball is sending signals to a laptop about the position of the ball. It was a project called Kicking Life into Classroom. Click. That means many students are not like you. They are bored by physics. And this is a way to bring students to physics. Also, they just like sports, for example. Another example, all of you know this, when an ambulance is passing you, the sound is changing. Why? The problem of this issue all over Europe is this is a curriculum issue for 6th graders, and physics starts with 8th graders. That means they have no chance to understand this. But when you are visualizing this, you immediately see, oh, the waves are different when the car is coming to you and is departing from you. Or another example, bird flight. You know, there are many migrating birds. There's even a bird migrating from North Africa to South Africa. Or even our white storks. They are flying every year 10,000 kilometers back down to South Africa. But you could visualize this. This is a biological issue. Let's have a look to a physics issue. Maybe all of you know this experiment, which is more or less in every science center. How is it possible to understand a word which is given in a very low density, 20 meters away? And here you see why it happens. Or another issue, which is all over Europe in the syllabus, and I always have my problems that the students are understanding this, photosynthesis. Without photosynthesis, we would not be here. This is the most important chemical reaction in the world, because without that, there would be no organic substance. How it works? A very simple experiment, which we did also with this Connect project 20 years ago. There is a plant within a closed space, and we simulate carbon dioxide. It means we inject carbon dioxide, and then, due to the diffusion, the carbon dioxide is randomly distributed. But when you are a very critical student, you immediately see there's a mistake in. Because when you look in the second row up there, there's carbon dioxide 350 ppm. Who of you knows what is the ppm right now? Sorry? Yeah, how many? Yeah, I wanted to know what is the current stage. It's not 350. All of you know this wonderful Keeley curve. When a chemist started 1958 measuring carbon dioxide, and by mistake he did not stop it. He just wanted to have the value for 1, and you immediately see it's going up. Now we have 430. And by the way, I just changed my talk half an hour ago, because 40 years ago I did my PhD in biology. And here you see a butterfly on the leg. Under the top of the palpi, there are about 200 sensillers doing nothing else than smelling carbon dioxide. And at that time, we had no idea why. In the meantime, We know why. Because when you look to the B was the reaction to the air in the year 85, because then I did my PhD. And you see a very small reaction. At that time it was the concentration 350 ppm. Nowadays it would be much more. And nowadays, if I would do my PhD, I would not become a science educator. For sure, I would apply for a carbon dioxide chair somewhere in Germany. Another example, how to introduce modern technology. In a university in the middle of Germany, there is a beehive. All of you know a beehive, where some thousands of bees are living. And when you go with a class to a beehive, it's a disaster because it's a black box. You don't see what's inside. And this beehive is full of sensors, and you could see the temperature outside and inside. And you immediately see, when you look to this green lines, the green line is the outside temperature, and the blue line is the inside temperature. That means bees are able to secure the same temperature all over the year. And then you can measure how many bees are leaving the beehive, how many bees are coming back, how many honey is produced every day, how is it dependent on the weather. It's an ideal inquiry-based learning lesson for 7th graders, because normally in 7th grade in Europe, this is an issue. Of course, since we are science educators, we always want to know what's going on in the brain of the pupils, of the students. And here, for example, is just the knowledge before and after. And when they do some hands-on stuff, and they do hands-on plus augmented reality. Without going into the detail, you immediately see there's an increase. I just show you 2 or 3 empirical stuff, not more, because this is a separate lecture. By the way, we published this 2008, progress on me, the visualizing the invisual, where we published about the augmented reality. Another example, bird flight. Is always an issue for 6th graders, more or less all over Europe. How birds fly. This is an example in a science center in UK, because UK at that time was still in Europe and was able to be partner in European projects. And here we could visualize what's happening when the angle of a wing is changing. And of course, via augmented reality, we can bring in additional information. I have a simulation about this, a very simple one. The cost of this experiment is about 10 euro, or let us say 15 euro. And you immediately see when you change the angle of the wing, something happens. And this means students can understand without having physics, because a 6th grader has no physics all over Europe in school, what's going on, why a bird is flying or why a plane is flying. Very simple experiment. Let me go back. Oops, here we are. This is a summary. You know, what's going on? There's a weight, there's a lift. What is causing this, this force that the wing is going up? By the way, in this wing, there were tish tennis balls in, and these tish tennis balls also were moved up. And then the pupils, the students immediately could see, wow, there's something going on. You can skip this. Another example, since you are physics students, I have a physics example for you. This is a nightmare, more or less for every student in the exam. Show the differences within these 4 circuits. When I think back to my physics education, it was always not good to answer this. But here you could help the students to say, okay, take one circuit, compare it with the second one, and you immediately see, wow, there are 2 similar ones. Then wait for the third one. And now coming to the probability, very likely you guess number 4 is the same as the other ones. That means it's a very abstract thing in a physics lesson, and you could help with this kind of simulations to understand what's going on, or to break the barrier that a student who is not aligned with physics maybe becomes interested in physics. Coming back to biology. When you have augmented reality and you go into the zoo, you can simulate, okay, what's going on with the body temperature. Another example, is somebody here with biologist? Okay, the penguins. The penguins, there are many penguins between the equator and the Antarctica. And there's always the question, where are the big ones and where are the small ones? And when you ask the students without lessons, for sure everybody says on the equator are the big ones, and in the Antarctica are the small ones, which of course is completely incorrect. Because there are 2 rules, the Bergman rules and the Allen-J rules. A small body is losing more energy than a big body compared to the volume. And therefore, the biggest penguin must be there where it is coldest. Then the next problem is how an animal survives the winter. I also have a simulation about this. Surviving a winter, there are several things. First of all, you could buy a coat. You could have a fur. Second thing is you could hide. The third thing is, the easiest thing is to hibernate, to wait until the winter is gone. So, and then you have the options. Insulation, body size, food, and where to hibernate. Of course, this is not a good issue in Greece, but today I left Germany with 9 degrees in the morning. There are other temperatures than in Greece right now. So, and then you could do forecast. Okay, we have a animal surviving outdoors, is very good insulated, has a big body, and needs some food. Okay, let's see what's going on. Okay, survives. Let's take another one. Medium insulated, middle-sized body, and the others the same. And here you see how the energy is losing during the winter. And sorry, it's in German, but it's very easy. This is not a good strategy to survive a winter. And of course, students could go even further and say, okay, our animal is not very well insulated. Okay, it will not survive when you do it this way, but we can say, okay, this animal hibernates. Hibernation outdoor is not good. That means hibernating, let us say, in a cave. Also not a good strategy, because we, as naked bodies, would not survive. But we could say, okay, let's do a good insulation, like a squirrel, for example. And let's say what's going on now. Surviving. Of course, this is not a thing of 5 minutes. The teacher has to include this or integrate this, let us say, into 2 lessons, 2 or 3 lessons. How to hibernate. So let's go on. Oops, let's go back to my presentation. It's here. Oops, where is it? Another empirical result about all these experiments, you immediately see there's not just knowledge going on. Of course, in the school, generally, you are tested, what is your knowledge? But knowledge is heavily dependent how interested you are, because think on your most boring subject. In my case, it was history. I don't know how it was in your case. And then in history, learning was a disaster. It always took me double or triple the size. And in biology, it was easy because I knew it already. When you have a big interest, you know it already. And here it's the same. You see interest, the effort, how you importance you judge a subject, or how useful you see a subject. Then you immediately see there's something going on, and it is affected by augmented reality, by the helping to help students to learn something better. Another one, a project which we did about 15 years ago, it was about astronomy. I was partner in this project. Also in Germany, astronomy is not in the syllabus. Nothing. But I was responsible for the evaluation. And at that time, we did a web analysis. And then in a web analysis, you could see what Google is doing when you are doing Google. Analyzing all the traffic which is going on. You know, how often you access a specific site. And here, it's a summary of them. It means we did the lessons during school time. During school time is difficult in Europe because sometimes school start in Germany, sometimes it starts 7:30. And in Ireland, it always starts at 9, or something like that. But you immediately see this is the curve for school time. That means the lesson took place during school time. Half a year later, something very strange happened. The students returned to the site, to the portal, and did it on their free time to interact with the portal, and to learn about astronomy. When you have such a result, you don't need empirical analysis, because it's very easy. If somebody is doing something voluntarily, it must be fun. It must be interesting. And I found a wonderful picture, so far as you know this, when we did the professional development 2012 in Geneva, there came an old guy around and talked to us. And this old guy, a year later, received the Nobel Prize. It was Mr. Higgs. That means it is always important to bring the expert and the education together. Education without the expert makes not really sense, but the experts alone, it's also difficult to talk to young people. So, and let me see how much time, I have 5 minutes left, isn't it? I come to the issue of our European project where we try to bring in artificial intelligence into a classroom. Why we are doing this? You know, in language and math, it is already fact. Artificial intelligence is in the classroom, but not in science. Why is it important? Because when a teacher is teaching something in a classroom, the teacher has 30 students. 30 individual students. Some good ones, some moderate ones, some bad ones, or let us say low achiever. What is the teacher doing? The teacher is planning her experiment for the middle ones. That means the good ones have some troubles, the bad ones have some troubles. So an artificial intelligence, we think, could help us to produce at least, I think the next one is it, to produce at least 3 different versions. That means to produce a lesson for the high performers, for the mid performance, which is normally the most one in the classroom, and the low performance. And I think the last one is the most, this one shows you some results which we have received in the meantime. Okay, let's start here. Low achiever. According to PISA, 40%. Low achiever do a hypothesis for the experiments, sometimes fail. They do the experiments and then they fail. Some low achiever, okay, come on, but they normally don't come to the final result because there are always problems in the meantime. The mid achiever, it's more interesting. We see some have a good hypothesis, but they fail to complete the experiment. But in the analysis, they are getting better, and maybe they come to a reflection. That means they summarize the experiment. And for the good ones, it's a little bit boring because they are going through the experiment anyway. What does it mean here? When the artificial intelligence realizes that there are troubles in the hypothesis, the artificial intelligence can support the student to go back, think again, come back, and maybe succeed with the experiment. The other one, let's say here, okay, a low achiever is doing very good experiment, but he's completing the experiment like a cook is doing a recipe and could not extract what is really the sense of the experiment and is not coming to the reflection sector. This might be the solution for bringing artificial intelligence also into a science classroom. In language is easy, because when you do a test and it is clear 50% of the words are not known, the artificial intelligence is bringing you to learn this 50%. Or in math. Math, you have a rule, and you apply this rule. And when you fail, okay, go back, explain the rule again, and go on. But in science, physics, chemistry, and biology, I always tell my student, it's a nightmare, because there is not just one solution, there are several ones. And therefore, physics seems easy, it is not. Chemistry seems easy, it is not. Biology seems very easy, but it's the most complex one, most difficult one. So I think I close my thing. Bridging the gap means bringing in additional tools, like augmented reality, which is now more or less standard. 20 years ago, it was difficult. Artificial intelligence right now is difficult. For sure, in 20 years, it is standard. Thank you very much.
So thank you very much, Professor. This is, let's say, the end of the keynote session. We will continue with dinner at the main restaurant at the center of the campus. So have a nice evening, and we will continue tomorrow with many interesting experiments and sessions. Thank you.